Okay, so in this video we want to extend things a little further to quartic functions. As I mentioned previously, all of the techniques we've now learned, they are all we need to deal with any degree polynomial function. It just becomes a bit more tedious the higher the degree gets, because you're just dealing with more factors, hence a more complex factorization process, not with any new steps, just needing to repeat the same steps a couple more times. So here we just want to have a look at a selection of examples, both solving quartics and also some graph sketching. So we'll just mention a couple of things about the graph sketching when we get to those examples. Alright, example 1, solve x to the power of 4 minus 27x equals 0. Okay, if we can solve by rearrangement, we want to do that, and by that I would mean a quartic equation where there's just one x in it. In this case, we've got an x to the power of 4 term and an x term, so we can't do that. Then, if we can't do that, we want to be able to use the null factor law. So make one side 0, factorise the other side, and use the null factor law. So one side's already 0. Let's factorise the left-hand side, which I'm looking for common factors first. X is a common factor. Leaves me with x cubed minus 27. Okay, and this doesn't factorise any further, or not easily, but we can use the null factor law from this point. So we know that either x equals 0, or x cubed minus 27 equals 0, which we can then solve this, adding 27 to both sides. X cubed equals 27, and so x is the cube root of 27, which is 3. So there are two solutions. The temptation here sometimes is to do this, to add 27x to both sides and then divide both sides by x. And when you do that, you assumed that x can't equal 0, and so you lost the x equals 0 solution. So we don't ever want to divide by x in the process of solving. Get everything on one side, factorise, and use the null factor law. Okay, example 2, solve x to the power of 4 plus 3x cubed minus 10x squared equals 0. So again, can't be solved by rearrangement because we've got more than one term involving x that aren't like terms. So we want to use the null factor law. So make one side 0, already done. Factorising the left-hand side. First step of any factorisation is to look for common factors, and there's a nice common factor here of x squared. Let's take that out. We're going to get left with x squared plus 3x minus 10 equals 0. And so factorising that quadratic, factors of negative 10 that add up to positive 3, it's going to be x plus 5, x minus 2, sorry. And so null factor law tells us that either x squared equals 0, which means x equals 0, or x plus 5 equals 0, so x equals negative 5, or x minus 2 equals 0, so x equals 2. 3 solutions to this particular quartic function. Okay, example 3, we'll just do this once. So here we have a quartic, cannot be solved by rearrangement. There's no common factors to be divided out, and so we need to factorise, and we need to factorise by finding a factor and doing some long division. Okay, so I'm going to do p of 1 is 1 minus 3 plus 1 plus 3 minus 2. So I've got negative 5 and positive 5 there, so that's 0. Okay, so that means that x minus 1 is a factor. Now let me give you two options here. What we can do at this point, like we would normally do, is we can divide x minus 1 into our polynomial, into our quartic, okay, and up here we're going to have a cubic. And so then what we'll know is that the equation is x minus 1 times a cubic equals 0, okay? And then we'll need to factorise the cubic, and so we'll need to go through all the same process again and factorise. So actually, probably a more efficient strategy at this point would be to see if we can find two factors using the factor theorem. Okay, so we found one, x minus 1 is a factor. We've got negative 2 here, so it can't be that complicated. Let's see if negative 1 works as well. So that would give us, positive 1, negative 1 to the power of 4 is still positive 1. Negative 1 cubed is negative, so this will make that positive 3. Negative 1 all squared is still positive 1. Negative 1 times 3 is minus 3, and then minus 2. So again, that also equals 0. So we also know that x plus 1 is a factor. Okay, so actually what that means is, again, we don't need to do two divisions here. We now know that x, I might write it over here, x to the power of 4 minus 3x cubed plus x squared plus 3x minus 2 equals 0, we know that x minus 1 is a factor of that, and we also know that x plus 1 is a factor of that, and then we know there's going to be two more factors, up to two more linear factors or a quadratic factor, okay? So we're going to need to divide to find what this is. This is what we're trying to find, okay? But actually the easiest way would be to divide by the quadratic. Okay, so if we combine those together, that's x squared minus 1. It's a difference of two squares. Even if it wasn't a difference of two squares, I would still combine them together to the quadratic, and then I would divide the quadratic into your polynomial. And again, this is where synthetic division falls down. Synthetic division doesn't allow you to divide anything other than linear factors. Okay, so that's why there's lots of reasons why I do prefer to stick with the long division process. Okay, so if we divide x squared minus 1, which is x minus 1 and x plus 1 combined together, then we're straight away going to get to this quadratic factor. We'll only need to do one long division by doing a little bit more work with the factor theorem to find two factors at the beginning. Okay, so what do we have to multiply x squared? So when you're dividing a quartic by a quadratic factor, you do need to be a bit careful about your columns. So x to the 4 terms, x cubed terms, x squared terms, x terms, and constant terms, so that you're subtracting like terms. So what do I have to multiply x squared by to get x to the power of 4? That's going to be x squared. So I'm going to put that in my squared column. And then I'm going to multiply x squared by this and write it down underneath. So it's x to the 4 minus x squared. Let's put that in the right column. So there's 0x cubed here, okay? Alright, so then we subtract. The x to the power of 4's cancel out. Negative 3x cubed minus 0x cubed is negative 3x cubed still. X squared minus x squared is plus 2x squared. And we bring down our next term. Okay, what do we have to multiply x by to get negative 3x cubed? That will be negative 3, sorry, what do we have to multiply x squared by to get negative 3x cubed? That'll be negative 3x, goes in the x column. We then multiply negative 3x by x squared minus 1. So it's negative 3x cubed and plus 3x. I'm going to put that in the x column. So I've got 0x in the middle there, and I'm going to subtract. 2x squared minus 0x squared is still 2x squared. 3x minus 3x, that's 0x. And then I'm going to bring down my next term, which is minus 2. And then what do I have to multiply x squared by to get 2x squared? Positive 2. Positive 2 times x squared minus 1 is 2x squared minus 2. And so we've got 0x, and it's all looking good here. We get a remainder of 0. So actually what we found is that that is that quadratic factor. Okay? And so we have times x squared minus 3x plus 2. And then we can look at factorising that quadratic. So we've got x minus 1, x plus 1. Factors of 2 that add up to negative 3. It's going to be x minus 2 and x minus 1. So actually fully factorised, we've got that repeated factor, x minus 1 squared times x plus 1 times x minus 2 equals 0. So we're trying to solve. Null factor law tells us that x minus 1 equals 0, so x equals 1, or x plus 1 equals 0, so x equals negative 1, or x minus 2 equals 0, so x equals 2. Okay, so as I said, you can do the process, you can find one factor, do the long division, get the cubic factor, and then repeat the whole thing. Or you can use the factor theorem to perhaps find two factors and then divide the quartic by a quadratic so you get straight away to the quadratic factor. I think it's probably a slightly more efficient method, assuming there are two linear factors that can be relatively easily found. Okay, example 4, we're going to sketch some graphs. So we're looking at quartic graphs. So shapes that we can get with quartic graphs, we've already looked at this basic shape, and that's if we've got it in turning point form, x minus h to the power of 4 plus k. Otherwise, we might have two turning points, we might have one turning point and one point of inflection, and there are some other things that can happen as well, which we'll have a look at in the last example. The point of inflection could happen first. Okay, so we can get all sorts of things happening here. In terms of number of solutions to a quartic, it's possible to get no solutions to a quartic if the x-axis sits right below the whole graph. Okay, it's possible to get just one solution in a case like that, or even in a case like this. Lots of different ways we can get just one solution. It's possible to get two solutions, Could be up here, could be here, could be up here, could be here, okay? And it's also possible to get 3 solutions. So we can get, and we should be able to get 4 solutions as well. Where am I going to get 4 solutions? Oh yeah, sorry, that was 4 solutions there. But it's possible to get 3 solutions if we just touch on there, okay? So we can get 0, 1, 2, 3, or 4 solutions when solving a quartic. Now all of these are positive quartics. That is, they have positive x to the power of 4. And they start up and finish up. If we have negative quartics, they go this way. Okay. Oops. And they start down and finish down. Same as what happens with a parabola. Okay. Happy parabola starts up, finishes up. Sad parabola starts down, finishes down. Sorry, I meant to draw that in green. Okay. So we're looking for, that's one of the early things you want to think about. Is the x to the power of 4 term positive or negative? And that tells us whether our graph starts up and finishes up, or whether it starts down and finishes down. We want to think about where the x-intercepts are, so we want to factorise. We want to be able to think about the shape of the graph at those x-intercepts. Do we have a turning point or a cut or even a point of inflection at an x-intercept? And then calculating y-intercept. Once again, turning points, unless it's in this form, turning points, and unless they're on the x-axis, we're not expected to calculate those at this point. Alright, so let's sketch this graph. So y equals x times x plus 1 times x squared minus 5x plus 6. Alright, let's think about our y-intercept, which is letting x equal 0. And this x out the front, he gives us a big hint there. So we're going to get 0 times, 1 times 6, so it's just going to be 0. Our x-intercepts, we let y equal 0. So we want to factorise. This is factorised. It's actually not fully factorised. This last quadratic factor can be factorised further. So let's do that. Factors of 6 that add up to negative 5, x minus 2, and x minus 3. Okay, so we've got 4 factors. So we're going to get 4 x-intercepts, x equals 0, x equals negative 1, x equals 2, and x equals 3. Each of those are linear factors. They're all to a power of 1. And so at each of these x-intercepts, we're going to be cutting through the x-axis. We're going to have that sort of linear behaviour in the neighbourhood of the x-intercept. It would expand out to be positive x to the power of 4. So we're looking at starting up and finishing up. Okay. It's not a parabola, but it's going to start up and finish up. Alright, let's think about what we've got then. So, negative 1, 0, 2, and 3. Negative 1, 0, 2, and 3. It starts up and finishes up. So it's going to start up here. It's going to cut through each of these. Okay. And so we should be able to get a bit of a sense of what's happening with the shape. So we're going to cut through there, we're going to cut through there, we're going to cut through there, and we're going to cut through there. In this case, this is a perfectly symmetric quartic, but they won't always be. Okay, it's just because the x-intercepts are symmetrically spaced. But so we could technically work out the turning points. They will the middle turning point will be halfway, but yeah, let's not make any assumptions. It's not necessary. So it's negative 1, 0. That's the origin. It's both the x-intercept and y-intercept. And that's 2, 0, and that's 3, 0. And there's our graph. Okay, example 5. Sketch the graph of y equals x minus 2 all squared times 5 minus x. Okay, first thing to think about, this is actually cubic. Sorry, didn't mean it to be quartic. Let's add an extra factor on there. Let's make it x plus 3 as well. Okay. Alright, so if we were to expand this out, this is going to give us negative x to the power of 4. The negative coming from that one. So you'll get x squared here times negative x times positive x, and so you'll get negative x to the power of 4. So that means the shape is going to start down and finish down. Okay. Our y-intercept, we let x equal 0, and so we're going to get negative 2 squared times 5 times 3. So that's 4 times 5 times 3. 4 times 5 is 20, and times 3 is 60. So a big y-intercept. They get big quite quickly with higher degree polynomials. It doesn't take much. You know, it's just 2 squared, and all of a sudden you've got an x-intercept of 60. Imagine if the squared had been on the 5, it'd be a much bigger x-intercept again. Sorry, y-intercept again. So x-intercepts, we let y equal 0, so we've got 0 equals x minus 2 squared, 5 minus x plus 3. Okay, so that null factor law tells me that x equals 2 is going to be a solution, x equals 5 is going to be a solution, x equals negative 3. Now the squared on this bracket tells me that we're going to have a touch or a bounce at that x-intercept. Sorry. The power of 1 tells me we're going to cut at that x-intercept, and it's a power of 1, so we're going to cut at that x-intercept. Alright, let's think about what we've got. So negative 3, positive 2 and positive 5, and a big positive y-intercept. Alright, 1, 2, 3, 1, 2, 3, 4, 5. So 5, 2 and negative 3. We already decided it starts down and finishes down, so it's going to come down here. That marries with the fact that we've got a positive y-intercept as well. And which one are we touching at? We're touching at this one. So we're going to cut at this one, and touch at that one. Okay, so let's draw in our shape. We're going to come up here, we're going to have a big y-intercept, we're going to touch here, and then we're going to cut here. Alright, so that is 5, 0, 2, 0, and negative 3, 0, and the y-intercept is 0, 60. Okay, and the final example here, I just include this to show you that there is a wider variety of things that can happen with quartics. So if we had this particular function here, we actually don't have enough algebraic tools to be able to sketch this quartic by hand. Okay, so we are a little limited still with what we can do until we have some calculus that enables us to think a bit more about the turning points. We're a little bit limited. So we're just going to use our CAS to sketch this graph just so that we've got a bit of a sense of the fact that they're not all going to be nice, neat examples like we've seen. Okay, so if I just go over to my graphing screen here and put in the function x to the power of 4, sorry, I didn't mean to press tab, plus 8x. Alright, and so we've got this here, so let's do some adjustments so we can see what's happening here. We absolutely don't need to see as wide as we can, so I'm just adjusting the window there. You just click once to select and once again to be able to edit. I'm just going to make that a bit more negative so I can actually see where that turning point is. Might make this just a bit bigger as well, might help me sort of see the shape a bit better. Okay, so what you can see here is we've only got 2 x-intercepts. We probably could calculate the x-intercepts by hand. Just to be clear about, if we were to calculate the x-intercepts by hand here, 0 equals x to the 4 plus 8x. Okay, so again we'd factorise, so it's a common factor of x, so it's x cubed plus 8. So please be clear that this is not the same as x plus 8 cubed. Okay, it's not telling you that there's a point of inflection at that x-intercept. Okay, so the cubed it has to be the whole bracket cubed to tell you about the shape. So null factor law tells me x equals 0 or x cubed plus 8 equals 0, which means x cubed equals negative 8. So x is the cube root of negative 8, which is negative 2. And if I edit this scale so we can see it better, yeah, it is indeed at negative 2. However, you know, 2 x-intercepts cuts at both x-intercepts. It still doesn't tell me enough about the shape to enable me to actually draw this. And you see here that it's not just a nice parabola, it's got this weird bend about it that, you know, we just don't have the tools to be able to find that. So in terms of sketching it, again, I did the calculating of the x-intercepts by hand. You can probably read them off the graph here, but once I've defined my function, it's nice and quick, easy over in the calculator screen. Menu 3.1 to solve. My function is function 1 in the calculator screen. Solving that equal to 0. I do indeed confirm that the x-intercepts are at negative 2 and 0. Let's just mark. So we're sort of cutting through there fairly normally. We're cutting through there fairly normally, and then we're getting this sort of kink happening out here that, as I said, we don't have any tools that enable us to actually sketch that. And to be honest, by the end of next year, you won't either. But I just include this here to illustrate that there is actually a much wider variety of things that can happen with Quartics. It's not just this or this or this or this. You know, there are all sorts of other combinations that can be going on as well. Okay, so you certainly wouldn't be asked to sketch something like that unless you had your CAS. If you have your CAS, pop it in, have a good look at what it looks like. Do adjust the window. You'll notice when it was only looking up to sort of 10, it was hard to see that real kink. Even if we went up a bit higher here to sort of 30, you get a much better sense of what's going on with the shape there. Okay, so exercise 6I for some sketching of Quartics. Please note that you should draw the graphs by hand, but you don't need to give the coordinates of the turning points at all. So I think the question suggests that you use technology to draw them. All of these graphs I'm setting you should be able to sketch by hand, and I would like you to practice doing them by hand, but you don't need to include the turning points. I think the turning points are included in the solutions, but I'm not expecting those at all.